hour to talk about soil because I could talk all day about soil. And you guys might think that it's time to sit back and relax. No, we're going to get excited. We're going to understand soil. We're going to start thinking about it. And there's no mystery about why this is the first topic for your Plan Your Land class series, because soil truly is the foundation of everything that you hopefully are about to embark on. One thing I will note is I tend to talk too fast. So Sarah, you just interrupt me when you need me to slow down and I will try and slow down. I get kind of excited. So please don't, moderators, hosts, feel shy about interrupting me. With that, I'm going to launch into it. All right, so what are we going to talk about today? If my slide will advance. Dun, da, da. All right, so we're going to define soil. No easy task. We're going to talk about soil inherent and dynamic properties. Very important to understand. We're going to talk about managing soils. I was asked to briefly talk about fire impacts on soils. I will touch on that. And then we're going to briefly touch on soils information and the ways you can learn about your soil through maps. So with that, I'm going to start with this. What are the three most important things I want you to turn your Zoom off tonight and think about it, or you tell your neighbor, or you text a friend and say, guess what I heard tonight on this silly class I signed, not silly, but this cool class I signed up for. I learned that my soil is my foundation to my land management, and I learned how to get to know it because that's super important. It really is from the ground up how natural resources conservation works. Soil is habitat. That is so important that I hope you guys take away from this, that soil is a thriving ecosystem. And then lastly, if you take care of your soil, it will take care of you. We should be working in partnership with our soil and not against it, because it can do some pretty amazing things if we let it do its thing. All right, those are our takeaways this evening. And we're going to start by defining soil. Now, before I launch into it, I want everyone to kind of on their own in their brains think about, what do I think of when I think of soil? You know, is it the mud on my boots that I have to sweep up? Is it that lovely earthy smell that I get when I dig into my garden for the first time in spring? Is it what's washing down my hill and I'm sad because I have erosion? So we're going to go really deep into what soil is. And you can't talk about soil without thinking about why soil is where it is and why it looks like it looks. We all know that soils come in different shapes, sizes, and colors. How come soils have different shapes, sizes, and colors? Well, it all fundamentally comes down to 5 soil forming factors. The 5 factors that in any place, think of standing in your pasture, in your garden, and you think about, why is the soil that I have under my feet here? It is because of the parent material. So the geology that formed it. Is it from bedrock? Is it from alluvial sediments that washed in from a river? Is it from a rock slide? Is it from sediment that was blown in on the wind of a glacial plain? Right? You gotta think about that. And then, where am I standing? Is it flat? Is it steep? Is it a little bit steep? Are my slopes going in? Are my slopes rounding out? Am I collecting water? Am I not? We're going to talk about that a lot, actually. And then then the organisms that live there. Am I under a pine forest? Or am I under fir trees? Am I in a pasture? Am I in somewhere that was burned historically by the natives who lived in the Willamette Valley? What's my climate? What was the climate when my soil formed? You know, haven't always had a temperate climate. The earth and the geology that is under Oregon has not always been in the, temperate Mediterranean climate that we have now. And we can see that when we have different colors of soils. And then time, how long has the sediment or the parent material been here with this slope and this climate with these organisms to make the soil that I have? So all those things come together and create the soil that is under your feet. And I promise you, there are 2 slides that have a lot of words on them, and this is the first one. And the reason I sat there and thought, I'm going to leave all that on there, because I want you to understand that it's so hard to sum up in a nice, concise sentence the definition of a soil. It's just too complicated. But I'm going to parse this out. I'm not even going to read this to you because the rest, I have a kind of a series of slides here that are going to break this down. So the first thing that a soil is a natural body. So that's number one too. When I'm talking about a soil and soil forming factors, I'm talking about something that formed through nature over time in a specific place. All right, so this is not that bag of topsoil you bought from Home Depot or from the farm store. This is, what's in your pasture or in your yard, hopefully in your yard. So what is it made of? It's made of solids, minerals and organic matter, and is made of liquids and gases. And so this pie chart is classic. The classic idea of soil is about 50% of it is solids, minerals that are composed of sand, silt, and clay. We're going to talk about that a little bit more when we talk about texture. And then that sliver, I don't know, can you guys see my arrow on my, Sarah, can you tell me if you can see my arrow when I'm pointing to something, or do I need to grab an arrow?
We can see it.
Okay, cool. So then this sliver, this is the organic matter. So all this mineral skeleton kind of the soil, and then this sliver of organic matter. And then the other half is air and water. And the reason you have these two arrows here is depending on how long it's been since the last time it rained, you have different amounts of air and water. So, hey, we all were in that atmospheric river that just happened the last couple days. Our soils, that air is going to be way down here. There's only a little bit of air left in our soils right now because they're super saturated. And right now that water is moving through the profile. So here's kind of a zoom up of, think of these big tan grains as sand, and then you've got little bits of silt and some organic matter in there. And then all this space in between is the pore space where that air and water is. So soil is kind of a diverse matrix of minerals, organic matter, liquids, and gases. So this matrix of organic minerals, liquids, and gases occupies space. And now I know that's so weird to say, that we have to say soil occupies space, but you got to think about soil as this, if you took all the soil away and you just had bedrock, and then you laid that blanket on top of it, and you think of that layer cake of soil going around different landforms, it occupies space. So we always take a profile cut and we look at a plane of soil. This picture here, we're looking at this solid sheet. Soil is not that way. It goes deep, it goes out and over, and we have to think about how it exists on that landscape and how it's draped over the contours of the ground. And then it has horizons, and it has, it is not uniform from top to bottom. Most soils are not uniform from the top till you get to the bedrock. There is some differentiation that's happening. And soil scientists really like to categorize things. We like to name things and describe things and put labels on them so that we can communicate with other soil scientists what we saw, because it was so cool. We want to tell them all about it. We got to find a language and a code to tell them all about it. So we name horizons with letters for the big ones that you see. So the top is the A and the B is the middle, and usually the C is getting close to the bedrock. If there was bedrock on this picture, it'd be an R. You might see this picture if you looked it up online that would have an R on it, but I took that off because I just want to talk about A, B, and C. So you have this mantle over the contours of the earth that is in 3 dimensions that have these layers. And why does soil have all these layers? Because there's lots of transformations that are going in that. If you think about times 0. So here, this picture down here is a river in Alaska, and this is a braided channel. And so you see places where trees are growing, and you see all these little channels through here, and then you see the back and forth of this wild river, and it has all this sediment here. So say something happens. Say there's an earthquake, not a big shock in Alaska for them to have an earthquake, and this, or a landslide or something, and this river jumps its channel and the whole channel moves half a mile to the west, for example. All right, well now all of this raw sand and sediment is times 0 for soil formation to start. And so when we think about it, every soil that we're standing on has had some sort of complicated times 0. And what happens at that point is plants start to grow and the climate starts to happen. So it's raining or it's snowing or it's a desert, so it's really dry. And things move around in that substrate and organize themselves into layers. As plants grow, they pump organic matter, so we get enrichment and darkening of that surface layer. Those organic material can move down channels that were created by roots. You have clay, soil clays. They exist on a spectrum, so they change their form. So you have clays that move and change form, and they drift down the soil profile. You have the sea horizon, which is that kind of matrix where it all started. It starts to kind of weather and crumble, and so you have things that are coming into the soil. You have things that are chemically and biogeochemically transferring around the soil. You've got stuff completely leaving at the bottom that's just gone, goes into the deep aquifers or runs down the hill. And you also have gases exchange. You have stuff that's coming out of the soil too. So all these transformations of chemicals and systems and gases and energy, carbon is energy, it's coming in and out. That's all happening. That's causing this differentiation. And when you have this differentiation, that's how you get all these colors and all these different types of soils. And as a soil scientist, you learn all about all the different ways that there's 12 soil orders. So across the entire world, we could organize every soil into a big bucket of 12. And then from there, it just whoosh. Oregon alone has 1,200 soils. It's a crazy number. Anyway, so as you can see here, this is what would be like a coastal soil. If you've gone on the Oregon coast and you look in the sand dunes, sometimes you see these color patterns. So here's an example where the iron, so all the brown color in soil comes from iron oxides that coat minerals. So most of soil is silicon, and that's coated in iron oxide, and iron is brown. And then in places where the iron is been dissolved over time, think high rainfall on the Coast Range, the iron washes out and you get red accumulation at the bottom, and then you just get bare silica grains, and that's why they're gray. This is a soil that if from Idaho, if I was going to draw the lines of the horizon, I'd have a horizon here. I'd have a horizon maybe kind of like that. I'd have a horizon here, and I bet I'd have a horizon here. And that is all because I can tell just from looking at the picture, the differentiation of those shapes and sizes and the different ways that the soil's layers have formed. All right, any questions about the definition of soils and how they exist, and a little bit about soil forming as I grab a quick sip of my tea?
Nothing in the chat box yet.
Awesome, thank you, Sarah. All right, we'll keep going with soil inherent and dynamic properties. This is where we're starting to get into the cool stuff. So now we kind of understand why soils are where they are and why they look like they look. But what do we want to know about them? So inherent soil properties. This speaks a lot to what I just talked about. They've formed typically over thousands of years. Some soils are millions of years old. Some soils are a couple hundred years old. Some soils, if you get a new lava flow in Hawaii, that soil is like, a day old. Anytime there's a plant growing, there's a little pocket of soil under that as it's starting to go in that lava. So when you talk about inherent soil properties, these are things like soil texture, the type of clay that's there. I did mention clays change, but it happens slowly over time. You're not going to wake up one morning and have a different type of clay in your pasture. The depth to bedrock, your drainage class. So that means if this is the top of the soil and this is the water table, how far up into your soil profile does that water table go? Does it go all the way to the top? Does it stay down here outside of never bothering you, or is it somewhere in the middle? So those are inherent soil properties. That's what we map. When you guys are looking at your soil surveys and your soil maps that Sarah's going to help you get, and then you go to Web Soil Survey and you dig into all the data and interpretations that are there, it's all based on inherent soil properties because those are repeatable and those are easy to map. I have a star next to soil texture because we're going to talk about that a little bit more after we talk about dynamic soil properties. So dynamic change, right? So these change with human management or natural disturbance. And I've bolded and made big human management because that typically is the force, the driver on why these soil properties are changing. And really, you all as land managers who are invested and interested in planning your land and being a more informed land manager, you are in control of many of your dynamic soil properties. So when it comes to inherent properties, you get what you got. You bought it. It's yours. You own it. When it comes to your dynamic soil properties, you're in control. There's things you can do that impact them. And I will specifically talk about organic matter content, soil biota. Those all, along with soil texture, drive aggregates, formation and aggregate stability. When you have good organic matter, you start to get infiltration and fertility. It can make changes to it, as well as your pH. I'm going to talk all about this stuff, and you guys gave me an hour, so I'm going to talk about it. I get to. All right, so soil texture, going back to our inherent property. This is the probably most important property that you would, as a land manager, you need to understand and know. What is soil texture? It is the percentage of sand, silt, or clay that is in your soil. So you could send it to a lab and they could give you the percentage of sand, silt, and clay. And because, like I mentioned, soil scientists like to categorize things, we say a sand is everything from a particle that is 0.05 millimeters to 2 millimeters. So here's kind of a graphical representation. I won't get into it, but we also separate sand into coarse sand, medium sand, fine sand. But just think of sand, everything from 0.05 to 2 millimeters. And we have sieves. We have stacks of sieves that we shake, and we can separate these particles out from each other. So anything, just for fun, above 2 millimeters is beginning of gravel. And then after gravel, we have cobbles. And after cobbles, we have stones. And after stones, if they're flat, we have channers. We go nuts. It's a party, right? All right, so after sand, we have silt fragments. Silt, if you felt pure silt soil, it feels like flour, like you have baking flour. And that is 0.002 millimeters to 0.05. Clay is everything less than 0.002. So they've got this green dot here for clay. Really, it shouldn't even be visible on this compared to these other size particles. It's so small. So your percentage of sand, silt, and clay is driving your soil texture. And, it's really important because depending on what your soil texture is, it's very important how you're going to manage it. A sandy soil is going to hold less water because it's just going to wash right through. And it's going to hold less nutrients because it's not going to have as many clay particles that have charges on their surfaces that hold on to those nutrients. A clay soil is going to hold more water because it's going to hold it tighter. But just because it's holding more doesn't mean that it's plant available, because it could be holding it so tight the roots can't get it off of the soil surface. Also, when you think about what's the perfect soil texture, so a loam is the classic, you can buy a loam soil. So a loam is a kind of nice mix of sand, silt, and clay, and that's giving you the best of all worlds. It's giving you the sand, which is giving you, it's going to let the water in, but it's not going to drain too fast. It's going to be nice and have some pores and aeration. And then clay is going to hold on to stuff for you, but not too much. So that's kind of why, a loam is what you want. So in the Willamette Valley, we are on this kind of part of the textural triangle: silt loams, silted clay loams, into clays. We do have some sandy loams and loams along the rivers, which are sandier, just in general, for you to know. So the next important thing to understand is your first dynamic soil property, which is soil organic matter. We could do an hour just on soil organic matter. It's amazing. So soil organic matter is everything that is alive or was alive in your soil. So that ladybug that crawled on that leaf and died yesterday, or drowned yesterday, right? From that ladybug that crawled on that leaf and drowned 2,000 years ago, and its body decomposed and turned into, resistant carbon. So soil organic matter is on a spectrum. There's all these fractions of organic matter and carbon in your soil. But from just a management perspective, it's easy to think of it as the fresh stuff, the stuff that's living, the stuff that's just died, the humus, the stuff that's, been dead for a while. So the pretty dead stuff, and the resistant stuff is like the really dead stuff. And we've always kind of categorized soil organic matter into these kind of fractions. Now, of course, as our science has improved, we're starting to understand that there's a lot more turnover between these pools than we maybe thought forever. But for today's purposes, you can think of it as the living stuff, the dead stuff, and the really dead stuff. And that is your organic matter. And it's always cycling between those pools. It's always kind of moving down that cycle as it gets decomposed. So why is soil organic matter important? Remember, it was that teeny tiny slice of the pie, but it packs a punch. A very small amount of organic matter is going to have a huge impact on a ton of your pretty important soil properties. Your water holding capacity, your aggregation, your nutrient cycling, your soil food web. So even though it's only a small amount, it has a really big impact. So we're really interested in how much organic matter is in your soil, how much used to be in your soil, and how much could you get in there now. And it's important to understand, talking more about genetic soils and soils that developed over time, that every soil has a stasis level of organic matter that in an undisturbed natural ecosystem would balance over time. So think undisturbed prairie, think undisturbed native coast range, think rangeland and Harney County. So all those soils developed under different climates and different parent materials and their different ages, and they've gotten to the point where they have a different level of organic matter. So we would never expect a soil in Harney County to achieve this with the same management, the same level of organic matter content as we would in a soil in the Willamette Valley, because they're just different soils. So when you think about your soil organic matter, you have to think about it in the context of what is the capacity, what is the inherent ability, or what did my soil have before it was manipulated or changed? And in the Willamette Valley, we have very forgiving soils. They started off with very high levels of organic matter. Compared to a lot of parts of the country, they still have very high levels of organic matter. But saying that, we still have lost a lot of that organic matter through normal cultivation and farming practices. So there's a lot of room there to get organic matter back in the soil. All right, so soil aggregation, I love it. I could spend an hour just on soil aggregation. You think, why is she so excited about clumps of soil? Why is that important? It's just a clod of soil. No, but it's like, it's so critical. It's so critical. I need to take a drink. I'm so excited to talk to you about it. So soil aggregation is where texture and organic matter meet. And that's why it's important. So here on this picture, actually this picture is funny. I start over in this corner. So you see a silt grain and you see clay, flat clay little particles here. And then you see microbial degrees. So you're seeing some sort of like something that, you know, a dead ladybug that went through the gut of a worm that was eaten by a microbe, and now it's some goo, right? So there's lots of gooey stuff in it. And that gooey stuff, when it's small enough, so we're talking really, really small here, you know, all these things have positive and negative charges, and they're starting to kind of connect in these positive and negative charges. And then you get, that's at the smallest level of that soil aggregate. And then you go up a level. So we're going from, you know, a degree here. So from the 10,000s to the thousands to the hundredths, right? Hopefully you're following that. So we go up. So here you go. This square just represents this little bit here. And now we're talking about something this size. So now you're talking about these little like held together charged things between this amalgamation of a mineral and an organic composite. And now we have, you know, maybe a worm ate that whole chunk and now it's coated in all these worm gut sticky stuff. And that's starting to hold together. And then you go up one, and now you have a root running through there, and you've got all these root hairs coming out. Root hairs are constantly exuding stuff. And so you get more things stuck together. And then you're also getting this cohesion, the next level up between roots just holding soil bits together, and fungal hyphae, which are the skinny strings of fungus, you know, miles and miles of that stuff. And it's forming this aggregate. And this aggregate is like the foundation of how your soil functions. I get really excited. And that is because all that comes together, and depending on your mineralogy and the length of time that you've had your soil forming, you get different shapes of aggregates. So you get single grain, this is like sand, not a lot of aggregates there, but still really cool because you get those soils that have those striking color patterns. Remember that gray and that orange? That really only happens in a sandy soil because the water has to move through so fast to move those things down. We typically will have soils in A horizons that have this granular kind of grape nut structure that blends to a blocky structure. So all these blocks are made up of all these little individual bits of aggregates. In some soils, form with shear, and so you get these prismatic structures. Some soils, platy structure, which it happens in, laminar layers like this, that can happen just genetically by pure development of the orientation of the clays, or it can happen when you take like a granular or blocky structure and you smush it with compaction. And then also we have soils that form that are massive, like there is no space in there, the water is not going anywhere. And that's why this is important, because your soil aggregation, which is then comes up with your soil structure, really makes a big difference for how your water moves through there. So you want to think about from the ground up, it's all about getting space in your soil, because you want water and air to get in there and have space. And why is that important? Because you need a place for all these organisms to live. This is the soil food web. I've seen many depictions of the soil food web. I decided to try this one with you guys because it's the most chaotic representation of a soil food web I've ever seen available, because soil food webs are chaotic. So let's step back and let's think about how this all starts. So imagine off to the side of this picture, you have a bright star in the sky. That is the sun. It is shining down, and you have plant leaves, pine needles. You have, think of your favorite flower, your favorite plant. It's got its leaves out there. It's catching that energy from the sun, and it's getting that carbon dioxide from the atmosphere, and it's doing that magic thing we call photosynthesis. And when photosynthesis happens, that plant is taking carbon dioxide. Of course, it's creating oxygen, but then it's taking that carbon from the carbon dioxide and it's building itself. It's building all its plant parts, and it's building its plant roots. But plants will take, depending on the plant, depending on the time of year, all that kind of stuff, 25% to up to 25% of all the carbon that plant is taking from the atmosphere and turning into different things. It's actually exuding through its roots. It is pumping the carbon out of its body into the soil. So that energy from the sun is going through a plant and out into the soil through a plant root. So energy, carbon, that's how carbon gets into the ground. You grow it with a plant. And so what happens next is along these root channels, you have these areas of like crazy microbial activity, because they all want that yummy carbon and they're ready to eat. And so then you start having this whole ecosystem form. And so you've got bacteria there and archaea, and they're munching on these, plant exudates, and they're getting grazed by a protozoa who's getting eaten by a nematode, who's going to get mowed over by a microarthropod, who's going to then poop it out its butt as a humic compound. And so all these arrows think of them as energy exchanges. And then at the end of the day, you got arthropods crawling in there, and you got birds and animals that are digging in the soil, and you've got worms who worms are like soil engineers. They not only make stable microaggregates, they also make pores in soils, and they push the walls of the soil and they make tunnels, and that creates space for soils. So the soil food web is this vibrant, robust, thriving ecosystem. And in this graph is 1 teaspoon of soil will have 100 million to 1 billion bacteria in an agricultural soil. Have yards of fungus. It'll have thousands of protozoa. It'll have, a handful of nematodes, but those nematodes are big. And then it's going to have arthropods and earthworms. So, you compare that, you can go ahead and look at the prairie and the forest soils. My favorite on the forest soil is where you've got in an agricultural system several yards of fungi. In a forest soil, a carnivorous, you can have several hundred yards in a teaspoon. You can have that much fungal hyphae. So these soil food webs, which are living in these aggregates, are just these thriving things. And that is why it's so critical to understand that soil is habitat. You as land managers, you're not just thinking of what's going on above ground. You have an entire ecosystem below ground. And you are all, as far as I know, terrestrial farmers, right? You are ranchers, or you've got pasture, you've got orchards, you've got gardens, and you're thinking dry land. So now you need to like zoom in onto the soil and think about it as habitat. So in this graph, we have a root, We have root hairs. We have these are the mycorrhizal fungi. We have a pore here, and we have an arthropod crunching down here. This is Godzilla, right? Compared to the size of this tiny little protozoa and all these little bacteria, right? And this guy's living in this terrestrial ecosystem. But then down here in this pore, this is an ocean for this little bacteria. And this nematode is, the Loch Ness monster in its loch. And this little pore has an oxygen concentration, and a carbon dioxide concentration and a pH that could be totally different than this little pore right here. And, it's there for like half a minute until Godzilla comes and crushes this sand particle, floods this ocean, falls down. And so you've got this aquatic and terrestrial ecosystem. This is the size of like 100 micrometers, right? So and you just expand that over your whole pasture, your whole garden. And soil is this thriving, dynamic ecosystem, and it all happens in this space. So as land managers, you are charged with thinking about, how do I get space in my soil, these pores, big pores, little pores, huge pores, teeny tiny pores, so that all this activity can happen. And what do we want this activity to do? What are we really getting at? So we're going to kind of sum it up here. We've got our inherent properties, we've got our texture, our location, our depth, our colors, and all that is being managed and manipulated. So we have these dynamic properties, our organic matter, and our soil aggregation. That all comes together into this natural habitat where we have microbe activity and diversity, and all that comes together into function. What is our soil doing? The basic things that we need our soil to do for us forever. And here are kind of the big basic functions of what soil is doing and what's happening in all those little spaces. Chemistry is happening in all those little spaces. Biogeochemistry is happening. Every bit of fertilizer you put on your soil is going through the body of a microorganism before it is getting to your plant. And it's transforming and becoming available. So they cycle nutrients, soils store carbon, they promote your root growth. The roots have to be able to move through that matrix. If it's too packed in, they can't get anywhere and they start growing out. So you want those roots to grow because your shoots can grow. We want to reduce erosion, so we want good, strong, stable aggregates that can handle a raindrop hitting them. We want the soil to hold the water. From an agronomic perspective, we're not talking about wetlands here, we're talking about agronomic perspective. We want the soil to hold the water, let it drain out, and then hold enough so our plants can grow. Because you think about after a rainstorm, what happens? That soil profile fills up with water, it starts to drain out, and it breathes. As it's draining out, it's kind of a pump where it's bringing that new fresh oxygen into the soil system. And all those microbes that are aerobic are starting to breathe. We want those big vibrant pores to hold water so you can resist drought. When you get all those kind of things, you start to get a stabilization of yields. If you're thinking like, 1,000-acre grass seed fields, that sort of stuff. And the more healthy and robust and diverse, vibrant soil food web you have, the more you have the ability to have competition. You want Game of Thrones in your soil food web because you want those good pests to outcompete those bad pests, and you want all the disease that's in there to be just a wink compared to all the other stuff that's going on. And if you have this vibrant ecosystem, you can get that. So that was a lot. Do we have any questions? Or do you want to wait to the end?
We do have a few questions actually in our chat box. So there was a lot of people that were really appreciating your enthusiasm and your beautiful slides. That's wonderful. And let's see, this one from Paul is asking, what is the most common limiting factor to plant growth in the Willamette Valley? After the rains, I guess it's available oxygen or pH or carbon nitrogen ratio, or is pH or carbon nitrogen ratio a concern?
I'll get into all that, but for the most part, in agronomic settings, the most limiting factor tends to be nitrogen and the carbon to nitrogen ratio.
Okay.
That's the quick answer, yeah. Think nitrogen.
Okay. And then from Ken, we had a little bit about the fires. So will we talk about the impact of the fires on characteristics of our soils and how to try to reverse them? Specifically, we have areas on the property now that resemble ash slurry that is 2 to 3 inches deep with water retention properties like clay, sorry.
Yeah, we will talk about that. I will try to go fast so I can spend some time on that for sure. And I even have slides and stuff, so I won't try to answer that right now. but thank you, Ken, for that question. We'll get there. All right, so I'll keep going. Managing soils. So this is where you guys as land managers need to start asking yourself some pretty big questions. Is my soil wet? How do I make my soil dry? That's a management question. How flat is my soil? Is it, I mean, it looks flat, but is it really flat? Because I just put my irrigation tape out and it's not flat. How can I get my soil to produce more? Was there a building here? Do I have water? Do I need water? Where did they park the bulldozer when they built the foundation of my house? And is that where I just decided to put my garden? Where should I not put my manure pile? If I want an orchard, where's the best spot? So you got to start thinking about all these things. And when you're managing soils, you got to think about the inherent soil properties. You got to think about any disturbance that might have happened on your land. And you got to think about the dynamic properties. Ultimately, at the end of the day, what is your goal? So I'm going to kind of go through these. Inherent properties, texture, drainage, slope, that kind of stuff. Altering inherent soil properties is often irreversible. I have people all the time who tell me, I've got this clay soil. I looked at the textural triangle. Can't I just add sand? Well, I ask you this, what happens when you add sand to a material that is a binding agent like clay? What do you get? Concrete. So let's not get buckets and dump trucks full of sand on our clay soils. That's not going to fix you and give you a loam. It's going to give you concrete. So the only exception to an inherent soil property that is reversible and you can go back and forth is drainage class. And that's with pattern tile drainage, which I'm not going to talk about in this, but you can take that water table, put in perforated clay, perforated plastic pipe. It used to be clay, terracotta clay. You can draw down that water table and move that water out of there. And then if you want that water table back, typically you could rip that plastic pipe out and your water table is not going to get drawn down anymore. That's actually what we do for wetland restoration. We go in and we rip out those old tiles and now we have a wetland again. So inherent soil properties. I kind of talked about that. You got to think about where you're standing. So if there's ever a place on your property that you want to do something, go out there and stand and look around. Am I at the top of the hill? You know, am I sitting up here under these trees? Am I on the side of a hill? Am I at the bottom? Am I near a stream? Because water's going to move through your soil and you're going to have different soils based on the top of the hill versus the side versus the bottom here. So you really want to think about where am I and what were the factors that might be why my soil is where it is and why it's acting like it's acting. And those are those inherent properties. So then you want to think about disturbance. How did they build my house? Did they scrape off all the topsoil, mix it up with the subsoil when they dug my basement, and now that's my yard where I want to plant my garden? Probably. Am I in my pasture? Did there used to be an old barn that's now collapsed? I'm in a forest setting. Did they do a lot of burning? Here's a picture from the 1900s where they're filling in a wetland. So this like think about the whole history of when people have been on your land, what has happened here? Because you might want to think about that when you're citing the best places to put things. My father-in-law lives on the Amity-Dayton Highway, and his property was an old army installation. Back Camp Adair wasn't always just Camp Adair. It was bigger than that during the World Wars. And so on his property, if you look at it, it just looks like a grass seed field. Oh my gosh, he's got old foundations. He's got just piles of gravel. Nothing that is the real soil. The only place that is the real soil is his garden patch where he's brought soil in. And so you couldn't use that the way that the soil map said because it's so highly disturbed. Now that's an extreme case, but you never know what surprises you might have out there. Now your dynamic soil properties. These are the things that have changed with management over time. So these are the things like you got to think about, okay, I've owned this property for a year. Do I know what they did before I owned it? Or maybe this has been in my family for generations. I got to go talk to grandma and see what they did. And also, maybe they did stuff that was great. Maybe things are working well. Or maybe maybe it was overgrazed. And so now I have concrete because it was, they had the animals out there when it was really wet and it squished all my soil aggregates. And now I don't have any pore space anymore. I'm very compacted. So the dynamic soil properties are your opportunity to make long-term management decisions that will improve your soil function. And we have a whole way to think about that. We call it soil health. High functioning soils are healthy soils. So these are the principles of soil health. And there's some of this information is in your thumb drive that you guys got. So principles of soil health: living roots, minimize disturbance, maximize diversity, and maximize soil cover. I'm going to get into this. I will make a quick note that when it comes to diversity, we talk about livestock as being part of maximizing diversity. Some people will actually pull livestock and having animals part of the soil system as a fifth principle of soil health. From an NRCS perspective, we put that in there with diversity because it's all biodiversity that's involved in the soil. So when you think about these factors, you're really talking about two big categories of things. You're going to feed your soil and you're going to protect your soil. You're going to feed your soil, you're going to feed that vibrant, healthy functioning micro habitat and all that ecosystem down there, and then you're going to protect it. You're going to keep that ecosystem where it is and intact. Now, how do you do that? So the next series of slides I have are the perspective of a gardener or someone who's doing a small acreage production garden. It also will apply to a small acreage organic farm. And then I'll also talk about this in the context of a pasture setting, because these principles that I'm talking about, these 4 principles, you can walk out onto your land and think about your system, and you can think about these 4 principles and where what you're doing fits into them and where you might have gaps. So living roots, how do we get living roots in soil? Cover crop. So living roots when you're growing your crop, and living roots when your crop is no longer producing, then you want to grow probably a cover crop. And really on small acreages, some sort of cover crop is the easiest way to get living root all year round. And in the Willamette Valley, there's only like 1 day a year, maybe 2 on a really cold year, where the microbial activity in your soil truly stops. We have almost a year-round growing season, and we all know that because the grass can grow even in December. So how do you know what cover crop? What do you know? How do you know a good cover crop to grow? There's a lot of resources out there. Sarah can point you to those. One of them is this Managing Cover Crops Profitably, which has all these charts and tables of what your objective is, because cover cropping is not something you just do for fun. Cover cropping is a lifestyle. You got to think about, what do I want my cover crop to do? Do I want it to add organic matter and pump carbon into the ground? Do I want it to protect me from erosion? Do I want it to get nitrogen in the soil, or do I want it to scavenge nitrogen? And you got to think about, when can I put the cover crop out there? Is it in fall, or can I do a summer cover crop? Do I have rotations? It's very complicated. People say, what's the best cover crop for me? And I'm like, get a cup of coffee and let's talk for 4 hours and we'll come up with like 3 options, right? It's a lifestyle. Cover cropping is wonderful. Highly encourage you guys to play around with it. But it's something to really think through before you put those first seeds in the ground, which is why we also say start small when it comes to cover crops. So maximizing diversity. Now, when you're in small production systems, some of the easiest ways to maximize diversity is through relay cropping. So while one crop is starting to senesce or it's about ready to harvest, you put in that next crop underneath it, or you put in that cover crop underneath it. So you're always having that diversity. Companion planting, if you're in small garden beds, you can do companion planting. But probably the most important thing from a small acreage standpoint is crop rotation. So maximizing diversity in time and space. So an example of diversity in time is companion planting or relay cropping. An example of diversity in space is that rotation. We all have heard about needing to rotate so you can break disease cycles and have different plants going in the ground, because I talked about how those plant roots are pumping carbon into there. Well, they're pumping carbon and they are have different flavors of carbon, and each kind of microorganism likes different flavors of carbon. And as you get it down there, you want as many different organisms eating as many different carbons so that you don't self-select for one kind of suite of microorganisms, and that's what you get with a monoculture. Now, I do need to go fast because I want to make sure I cover a bunch of stuff. And also disturbance. So when from a garden setting, you want to minimize disturbance. It's hard to not disturb at all at a small scale. If you get up to a big enough scale where it makes sense to have bigger machinery, you would have drills, like no-till drills and that kind of stuff, like teeny tiny ones or big ones. But from a gardening perspective or a small acreage perspective, it's all about what tool are you using, how deep are you going, how often, how much, is your settings correct, and are you weeding and you can just disturb the top inch, or you got that thing set so you're like chugging up 8 inches of your soil. if you need to kill your plants, are there different options like solarization versus just rototilling everything up? So it's about mindful disturbance, understanding that every time you disturb the soil, you are ruining and destroying your soil aggregates, and it takes time for that stuff to get back and form again. So you're losing some of that soil function as you disturb. So maximizing soil cover, that's with cover crops, again, a living soil cover or mulch or relay cropping or compost or something that's going to protect that soil surface. From a pasture situation, and I apologize for our pasture people in the room, we are going to skip this slide, but it is available for you. All I've done here is I've taken those same principles and put them in the context of how you would manage a pasture utilization, mixing multi-species pasture mixes, minimizing disturbance, that sort of thing. So I apologize, but I want to make sure I have time to talk. And this just is speaking to that all of these management is happening on a spectrum. So when you think about your system and trying to figure out how I'm going to hit each of those soil health principles, it might be easy to keep your soil covered, but really hard to not disturb it. Doesn't matter, try it. Figure out what's going to work with you and take baby steps to try and get those soil health principles applied to your land so that you can start to have higher functioning soils. It's a journey. And why? Because this gets us to a goal. What do I want my soil to do for me? I want my soil to be resilient. I want it to protect my plants. I want it to have good water flow storage and clean those waters. I want it to store nutrients. I want to have my temperature buffered in hot summer days because I've got shade on my soil. And I want good structure and stability so that my habitat has a place to be and a place to live. So yes, I rushed, but that is because I wanted to make sure I get to fire. And I'm excited, but fire is one of those dynamic ways that dynamic soil properties change because of a natural event. So fire impacts on soil. And Sarah, I will say if we run out of time, I'm happy for you to export the chat and for me to answer any questions and through email later. So what does fire impact on soil? Fire impacts all soil properties, chemical, physical, and biological. So we've talked about physical, biological, and chemical properties all this evening. So how a fire impacts that, how much it impacts that is all about the duration of the fire, how long was the fire there, how hot did it get, and those two things impact the depth at which that heat moves down the soil profile. And I know you guys are going to have some people talk to you who are more experts at this than I am, but I just wanted to give you some of the science. So from a soil temperature perspective, when you have a fire, and an average forest fire, I looked it up, will get as hot as 800 degrees Celsius. So when you're at 100 degrees Celsius, you start to get seedling death, bacteria start to die. When you're between 200 and 300 degrees, organic matter starts to burn up and get distilled destructively. You start to get volatilization of phosphorus and phosphates. You start to lose amino acids. You start to build char when you're at 400 or 500 degrees. And then as you get up to 800, you're volatilizing potassium. So volatilization is it's burning off as a gas, these nutrients, and you're changing your organic matter and it's turning into different compounds. So that is very characteristic for what's happening under these high intensity, high burn fires. So depending on how your fire burned and the duration of time, it's going to get to a different temperature. So you can have gradients of this across your property, depending on how the fire moved across your property. So here's a graphic of how kind of fire works. So fire intensity, a crown fire where the whole tree is burning versus a brush fire. So you've got heat going out with the flames, but you also have heat going down into the soil. And that's where you have conductive and radiant heat. It's burning off that organic litter and it's moving that heat down into the soil. And that's where you start to, when they do burn severity, they're looking for how far down in the soil and what change in those soil properties that they can measure to show you how severe your fire was and how that impacted your soil. And that's where you start to get into those ashy slurries that are then, you can have hydrophobicity. So that is where, you get, so soil, we want the water to go in. If you have a hydrophobic layer, phobic being fear, hydro being water, it means that the water from rain is going to go into that soil and it's going to create, there's a barrier now that will repel the water and it won't go down. So that forms when the fire is hot enough, long enough, that the organic matter in there volatilizes into different it changes and is vaporized into substances that are hydrophobic that start to move down the soil profile and the temperature gradient. And that's what this picture is showing you here. You've got an unburned bush, you got a fire, that bush is gone. Now you've got char here, and now you have this litter that's totally burnt off, and the fire is less hot as you go down. So you get to this point where there is this this water repellent layer, this hydrophobic layer that is in the soil. You get this kind of, it can be, I've seen ashy slurry, I've seen just powder on top of it. So what do you do about your hydrophobic layer? Well, it's all about scale, unfortunately. So if it's over vast acreages, there's not a lot you can do. If it's something that's you can treat on your own scale of your property, this is the second slide that has a lot of words on it. The recommendations, and this is straight out of extension publications, is try to, erosion is going to happen, so you try to catch that sediment to slow it down. On gentle slopes or something that is at a scale that this is practicable, they recommend trying to break up that hydrophobic layer, which may or may not be possible depending on how deep it is. And then what you want to do is you want to get some seeds out there and growing, because those roots hopefully will help break that up, and it's going to capture and keep that soil there. They also talk about straw, scattering straw, or building fences and silt dams. I know from an NRCS perspective, we do post-fire recovery, and we help people get everything organized and cost share to fly on aerial application of seed. And depending on if the seed takes or not, that can have more or less success, but at least we're trying something to stabilize that soil. Over time, depending on how thick that hydrophobic layer is, it'll disappear. So roots break into it, microorganisms start eating those compounds, and that hydrophobicity does not persist. It will break down, depending on how thick it is, again, over time, sometimes up to a year. So when it comes to fire, this is all from one of these seminal papers about effects of fire and soil properties. You can't do much about losing your top litter it just burns away in a fire. So when you think about it, when you're doing post-fire recovery, the idea is to try to get something growing on that soil again as soon as possible, to start holding the soil in place, reforming those soil aggregates. You also have to understand that depending on the duration and the temperature of that fire, you're going to have lost carbon, nitrogen, sulfur, and phosphorus because of volatilization, and you're going to lose those minerals and soil, essential plant nutrients are just gone from that system. And of course, nitrogen is a huge limiting factor in our natural forest ecosystems. So you got to think about how, if I'm going to do an aggressive post-fire recovery, how can I get nitrogen back in that? And that comes in a lot of different ways. It all depends on the scale that you're working, how much money you have to invest in it. So it might be, instead of trying to you don't typically use fertilizer over large forest acreages, but you might try to grow plants that might be able to be legumes that are going to fix nitrogen. So again, I'm not an expert on all these topics. There's people who devote their whole careers to it, but from a science perspective, I hope I've given you kind of an overview of what happens post-fire. So I know there's a lot of questions, but real quick, obviously, not super quick, talking about soil surveys. I think this is important for your homework. I don't know if there's a test, but maybe there's a test. So again, kind of abrupt change in topics here, but I do want to cover what a soil survey is. A soil survey is a map of soils. It includes soil descriptions, locations, it includes their suitabilities for and limitations for management. And it's meant for people like you, people who are managing land. It is a collection of information of soils. I won't talk about how they make them, but just know that you can read the slide and you can figure out how a soil survey is made. Just know that a person went across the landscape that you are living on, either physically or from the neighbor's place, and have organized the landscape into repeatable patterns of soils. And a good example, if you think of the Willamette River, from the Columbia down to Lane County, where it's coming out of the mountains near Eugene. So, you have a river system moving through there, and you can expect that on the edges of that river system, whether you're in Lane County or Multnomah County, you're going to have the same soils across, north to south because they have the same soil forming factors, that first slide, that first foundational slide. And so what soil scientists do is they find those repeatable patterns of soils across the landscape on different landforms, and then they name them. And they name the soils and they organize them into map units. And a map unit is always going to have a symbol, have named components, and it might also have this other information like surface texture, it might have a slope group, or it might have some kind of description like very steep. And this is important because when you get your soil map, you want to decode it and read what's in there. So if you're on Web Soil Survey, you'll get a soil list of soil map units that looks like this, or whatever Sarah gives you is going to have a legend that's going to have the name of these soil map units. So major components are what's named in a soil map unit. It's the dominant soil that you'll find in that soil map unit. Typically in agricultural soils, we have single soil series, like a Camas, gravelly, sandy loam there. That map unit is made mostly of Camas soil, which is a gravelly, sandy loam. This is one of our river soils. You can also have multiple named soils in it. So our forest soils tend to have more than one soil named in it because they are so complex on the landscape that at the scale mapping, it's been possible to draw a single line around them. It could have higher texts, and people get a little confused when they see things like this word here to say that it is xerocreps or haploxerols. Basically, that's soil taxonomy. That's going deep into the science, and that's saying that that soil occurs so infrequently that we didn't bother putting a name on it. And that's typically what you see right along like a river and that sand bed that's growing plants, but it's so different layer deposits and all that kind of stuff that they haven't taken the time to find a repeatable pattern. So they say, we're going to call it this higher, we're going to put it in a bigger bucket. That's a broader bucket. And then you also have some things like miscellaneous areas. So water or a river or a pond or rock outcrop is going to could have a delineation around it. And that's a soil map unit. So soil map units always also have minor components. These are the parts of that soil map unit, that polygon that has a line around it. It's not the dominant soil, but it's important enough that the person who made the map wanted to bring it to your attention. And these are typically in the Willamette Valley. You find that the minor components are the soils that exist in that map unit that have a different drainage class. So if you have a Willamette silt loam, which is a beautiful, well-drained soil, but then in those small little swales, where the water pools, you might have a Dayton soil, which is going to be a poorly drained soil. So if you were that land manager, you'd want to know that, yeah, the majority of this map unit is this beautiful Willamette soil. But hey, I do know I've got some of those swales in there. I know as a land manager, I expect to have more standing water there. I need to manage that differently. So the minor components call out differences in soils that make a difference from the management perspective. Here's a fun little representation. This is in Eastern Oregon. Here we have our soil map. This is what you would see on a piece of paper on your computer screen. Pay attention to this green triangle in the middle. Here we have it on the aerial photo. Here it is with the topo map. So this is the USGS topo maps, which show scale of slope. So here we have, again, our flat triangle in the middle. And then we start to see patterns here where these lines that are close together on topo map are steep and lines that are far apart on a topo map are not steep. So we start to see areas here where this triangle is flat and then we have these steep side slopes. And then you can imagine that here in this area, you're standing on the top of a plateau. Now we're actually going to stand on this landscape. So this triangle that you saw on that soil map, that is this triangle here. That has a map unit that has properties and interpretations and limitations. And these steep slopes, like this 157, that's a soil. That has named dominant soils. That has properties and interpretations and suitabilities and limitations for use. And then you have your plateaus, which same thing, properties, interpretations, suitabilities, limitations for use. And so that's how you think about, from a perspective of a landform, how we organize that landscape, literally draw lines around it, and then give you information about it to use. So this is my last slide. And I'm going to finish hopefully on time. A word about map scale. So if you've gone into Web Soil Survey and you've like zoomed into just your yard, and your yard is maybe an acre, you're going to get this warning. And that is because soil maps were made at a much higher scale, typically 1 to 20,000 or 1 to 24,000. What does that mean? 1 to 20,000 means that 1 inch on that map is 20,000 inches on the landscape, not just the size of your yard. So we create soil maps, and they're very accurate at the scale at which they were made. So if you zoom into just your yard and it's at a scale that is way too small for the intent of the map makers, it might have a named soil, but at the size you're looking at, that could be wrong, because the majority of that map unit, which is way bigger, your house is just one little dot in that. For the majority of that map unit, then we have that soil. And to put it into context, I showed you all the soil maps that have lines on them. At 1 to 20 scale, 1 to 20,000 scale, that line itself is about 35 feet wide. So if your yard is 90 feet wide, you know, you could be on a line, just the line on the map is a third of your yard. So that's some perspective for that. And with that, I say it's the end, but for you guys, it's really the beginning, because now you understand soil, you know what soil does, soil is habitat. You know that if you take care of your soil, it's going to take care of you. And you guys can start to use this foundational knowledge of understanding how your soil works as you go through this exercise, and you know, think about planning for managing natural resources on your land. Whew. Questions. Sorry that I had to go fast there at the end. I wanted to cover it all.
That was awesome. Thank you so much, Corey. And we got some comments to that effect on the chat box too. So thank you, thank you. We do have a few questions. We'll start with ones about burned soil. So I'll read these off to you. We have burned soil. We'll do test and try cover crops. Wondering about additives, as this is under an acre, and there is a sale from 10 Rivers Food Web in Corvallis. Green sand, sulfur, other additives which may be needed. I was wondering, as a gardener, but may want more for the burned area. Bulk buying, sold at cost. Pick up at Benton County Fairgrounds, February 6th. Do you recommend adding additives to burned soil?
So burned soil is a totally different scenario than I would say for any other management thing. So anything that you can do right now for your burned soil that's going to get organic matter, life, and nutrients back there and protect it from erosion and start to try and kind of put back what was volatilized, I would say go for it. If you're at a scale that you can do that, afford it, and then have the willpower to spread it out, I would say go for it. With any kind of additive or any kind of thing that you buy and put on your ground, I always caution people to understand, what is the source? Is it clean, weed-free substrate? Know what you're buying. Know what the carbon to nitrogen ratio is, because if it's a really high carbon to nitrogen ratio and then you try to put a plant out there, you know, those nutrients are going to be tied up and it's going to be hard to grow. So it's hard for me just hearing what you want to buy to know if that's the right thing. But I would say anything that you're going to buy that is going to act as a mulching in it and to give back some of those elements that might have been volatilized is probably a good idea. I would certainly reach out to OSU Extension or to the vendor to see, they will know their product, to know if it's been used in that kind of context before and if it's really the right thing for you.
Excellent. Okay, so Jenny Meisel mentioned that we do have burn severity maps available for the Beachy Creek fire area. So if folks whose property burned want a burn severity map to get a better idea of what's going on in their soils, they can either contact us, or you can put your name right now into the chat, the group chat, and we will get those to you. In a burned rocky forest areas with little soil, does the risk of erosion increase or decrease?
So really the risk of erosion in a burned area is most highly correlated to slope, how steep the slope is. So, and rocks, actually, if you truly have rocks on the surface, that actually kind of acts as armor. So from a erosion perspective in a post-fire situation, the driving factor truly is going to be your slope steepness, and then of course storm intensity and duration when rainfall events happen. I think that might have answered that.
Okay. What are the benefits of soil, or to soil of fire applied as a prescribed burn?
Okay, so the other side of the coin, I talked about, those slides are very wildfire specific. So when you do a prescribed burn, what they're doing there is a low intensity, short duration. So you're usually not getting on that temperature scale that I showed you anywhere near those orange red temperatures. It's funny to say, but it's like it's a cool fire that kind of creeps across and burns through. And that's what the ecosystem developed with over the thousands of years, not these high intensity catastrophic crown type fires. So when they do prescribe burns, what they're trying to do is, burn fuels and also so when that volatilization happens, it's also like a big flush of nutrients too. So under the right circumstances, it can be a benefit to the ecosystem. And that's why they do prescribe burns for fuel load and to try and mimic how fire used to be. And then, when a wildfire comes through, they can tell based on burn severity, places that have had a prescribed burn versus not, because the fire behavior is different.
Oh, interesting. So is the burn severity less in places that have had a prescribed burn before that?
Yeah, yes, typically that, and it's a fuel load thing too. So we have examples where we've done massive conservation efforts where we've done fuels reduction, like mechanical, we remove all those kind of ladder fuels and stuff from, east face of Baker County. There's that big mountain range there. And so they had a fire come through and it was like the classic example. Here's this crown fire coming through, high intensity, big fire, and it hit that treatment area and the fire dropped and it just crawled along the ground and it went across the treatment area and they got back to the high fuel loads and boom, it went back up to a crown fire. And that's what a prescribed burn and all these mechanical treatments are doing when we talk about wildfire mitigation or catastrophic wildfire mitigation, is trying to change the forest above ground matrix to more mimic what would have been there before all of our human interventions, so that fire behavior is different.
Excellent. Awesome. Thank you. Let's see. Another one. Does just ash fallout change your soil or the pH?
Yeah, so ash itself is actually very high in potassium. So I'm not sure exactly what it does to pH. I would have to look that up, but it does alter the chemistry. So sometimes that's why you can get a production benefit from not a high intensity fire, but from some prescribed burn. One of the benefits is you get this ash layer, which is nutrient rich. I can't speak exactly to pH. So if you email me that question, Sarah, that's something that I can answer later, because I don't want to say it wrong.
Awesome. Okay. All right, I can do that. Another one, they have burned soil. Nope, that's the wrong one. Sorry, let me. So here's someone asking about rototilling, whether rototilling makes a pan, and the land has been driven on for a long time, so there's a lot of compaction, and how to economically add organics to a soil like that.
Okay, so when you have a compacted soil, I like to think of it as, so you could grow these like deep tap rooting cover crops. And if you have enough time, a cover crop, think of a ryegrass or a taproot, like a brassica, like a daikon radish or something. Those are often strong enough to over time break those compacted layers. And what those fibrous roots do is they do find microplanes of failure in that compacted zone, that if you stop doing the activity that's causing the compaction, like driving on it, or you change your livestock intensity, over time a cover crop can break up a compacted soil. It takes time. So what I tend to talk to people about when they're dealing with a compacted zone is a big intervention to set you up for long-term success. So if you have a rototiller, if you have some kind of equipment that you can, get into that compacted zone and break it up, that's great, but you have to have a plan, because if you break that up and then just go about your business, it's just gonna compact again and get worse and worse and worse and worse, because a rototiller will cause compaction. But if you go in with a rototiller and you break up that compacted zone and then you plant a cover crop that has a deep fibrous root system, there's lots of examples of them. They're not like a ryegrass. A lot of people don't like to do grass in their gardens. So you have that layer broken up and you immediately go in with a cover crop that's going to start to form those soil aggregates. What you've done is done a one big intervention that sets you up for long-term success. The trick is though, you can't rototill the next year. You have to give it some space, some time off from disturbance, driving on it, tilling it up to get the benefits of that. And that's why it's a little bit tricky in a garden. So in a garden, it's hard to get organic matter in the ground. So you can grow a cover crop that's going to pump carbon in. You can put a mulch or a compost on top. If you have time, you let that decompose, it's going to work its way in. A lot of people like to use equipment to mix them together. And that is fine. You just got to think about what you're doing, because if you're going to be mixing that organic matter into your mineral soil surface, are you doing that every year, or are you doing that like every other year? And so you're giving those aggregates time to form. I work with Nick Andrews from Oregon State University Extension, and he says that you can make up for a lot of your sins of tillage by good cover cropping and by adding good organic matter. So what happens over time though is you change that pool of organic matter that's growing in your system. So you're going from fresh, new organic matter that you're adding annually, and you're losing that long-term resistant organic matter that's been there for thousands of years. So you're shifting that carbon pool. From a production standpoint, you might be getting the benefits of the water infiltration and the nutrient cycling, that sort of stuff. You just have to kind of think about what's going on. And as far as economically getting organic matter into your garden, the cheapest way to do that is some cover crop seeds. Grow a cover crop over the winter that's going to winter kill, lay down, and then now you've grown a whole crop that's harvested carbon from the atmosphere, and it's ready. Its whole purpose is to go in your soil in place. You don't have to haul it anywhere. It just grows there. It's great. Plants are amazing.
So do you recommend tiller radish or a daikon, I think it is, for that kind of work? Is that?
Yeah, for a compacted zone, yeah. They sell cover crop mixes that, soil busters, that kind of thing. I've seen those radishes where it'll grow and it'll grow sideways, but it's all about just thinking about what is the condition of my soil, how deep is my compacted zone from the top of the soil down, how thick is it, and do I need to treat it everywhere? If I'm growing in garden beds, maybe I want my rows that I'm going to walk on to stay that way, and I just plant something there that's going to keep the soil from eroding, and then I really focus on where I'm actually going to grow the plants. So it's really just kind of how you have things set up.